after looking at B-splines, we finally derived one spline curve, and but the more important thing was to note that even though it was defined piecewise, right, it is providing you with continuity up to order k minus 2, where k is the order of the curve. Right, so if you have a quadratic curve, then I will get tangent continuity guaranteed at the junctions, the knot points. And if I have cubic, I'm guaranteed to get curvature continuity at these knot points. And so that's a remarkable thing to have, that while it is defined piecewise, you still have the continuity you want, right? And we also showed that in the limiting case, right, the spline converts to degenerates to the Bezier curve when k is equal to n plus 1, right? So we showed, I mean, more by induction, that because the knot vector reduces to a single segment, right? When I have k to be equal to n plus 1, then this is what I get, and therefore I get a single segment which has the property of endpoint interpolation and tangent to the first and the last polygon leg. And therefore, we know that it is a Bezier curve. And because it is a special case, all the properties, the general will be, a superset of the properties of the particular, which is the Bezier. And therefore, the spline also will have the same properties of endpoint interpolation and tangent to the polygon legs and the convex hull property. But the good thing about this is that in addition to the tangent convex hull property with all the control points, it has a more restrictive or a tighter convex hull property, meaning that each segment will also follow the convex hull property. So if I look at this curve here, then each segment of this curve will lie inside the convex hull of the segments, the control points that define that. So the first segment is defined by the first 3, second by the next 3, and so forth. And you will find that each of those segments lies inside the respective convex hull of the respective k control polygons, right? And that's a property that gives immense predictability and intuitive feel to the shape of the curve, no matter what control points you use to define. Okay, so with the spline, then we have addressed both the limitations of the Bezier curve, and we are able to get similar properties, if not better properties than that of the Bezier, and therefore we have a good solution in our hands, right? We have a solution that answers most of our queries. Now that was with arbitrary shaped curves which do not have an analytical form, right? And I left you with this question at the end of the class that, if I now want to use a spline form or a spline representation for a known curve, right? Known curve is something for which you have an analytical expression already with you. In this case, we use the example of the quadrant of a circle, right? An arc of a circle, which is at 90 degrees to the quadrant, and a very specific case, origin at the center and the two endpoints are start point and the end point of the arc are given. And the question asked was that, can we write down a spline representation for this particular entity, right? So I'm going to start with this particular question in today's class. So let me just, before that, ask if there are any questions on whatever we have done so far in the previous lectures. Any questions? Okay. If there are no questions, then let me restate that question I had asked you, which is, if I want to find a representation for a curve, which I know is an arc of a circle subtending 90 degrees at the center, which is the origin, and my radius of the circle is unit, can you now give me a representation, a spline representation for the curve? Right? So what do I need to answer this question? What is the information that I need to answer this question?
The number of control points.
Okay, so n. What do you think n should be?
So 4.
3.
Okay, so we have two choices. So I'll put both here, 3 or 4, and we'll resolve this in a minute. What else do we need to specify? Remember, we had made this list of parameters for the spline curve, right? One chart was there. So the next thing that we need to prescribe is K, right? So what should K be for a circle? Any thoughts? What kind of a curve is a circle? What degree typically is it considered to be? Okay, let me then ask, set up a process of elimination. Can K be 2? If K is 2, what is the degree? What kind of a curve do I have?
It's line.
It's a line. So I guess clearly that's not an option.
Yes. 3.
3? 3 will give me a degree of 2, which is quadratic. That's a possibility, right? I hope you agree, because the circle is a curve of the type that, right? It's a quadratic curve, second degree curve. And therefore, K equals 3 is a distinct possibility. And since we always try to start with the smallest degree that we can get away with, right? So quadratic is the choice. So therefore, K is 3, right? Now that you have chosen K, the next thing to choose is X, but that depends on your choice of N. So now let's go and revisit N. How do you choose N now? If K is 3, what is the smallest value of N that you can have?
Two.
2. Why is that? Because this is N, and I think you guys were saying the number of control points here. So
Yes,
the number of control points here is 3, and that's the minimum number you need for a quadratic curve. And so if I choose N to be 2 and K to be 3, my knot vector will turn out to be that, right? N plus K plus 1, that is 6. First K are 0, last K are N minus K plus 2, N minus K plus 2 is 1, and therefore this is. So in some sense, we are starting with a Bezier curve, but that is okay, right? The only thing now left is that you have to define the PIs, the control points. So how many PIs are there? 3, right? P0, P1, P2. How many of them do you know?
2.
2. Why? The 2 endpoints. The curve has
Yes.
to interpolate the first and the last point, and they are already given to you. You know that the curve has to go through 1, 0 and end at 0, 1, and therefore these 2 points are known. So this is P0 and this is P1. So the only question mark list that is there now is on P1, right? So what should P1 be? What do we know about P1 now? What we know about P1 is from the properties of the spline, of the Bezier, right? If I have 3 control points, right, and the curve has to be interpolating, but it is also tangent to this leg and tangent to that leg, which means that in this case, P1 lies on this line, P1 must also lie on this line. And therefore, do you have a choice of P1 now? Can you choose P1 or it is fixed? As you can see here, because of this property that the curve must be tangential to the first polygon leg and the, oh, my numbering is off, sorry. Yeah, the first polygon leg and the second polygon leg. So P1 must be somewhere on this line because the curve is going like this and this line has to be tangent to that. The polygon leg has to be tangent. And P1 must also lie on this line because it is tangent to the last polygon leg. And therefore the two will intersect only at one point and therefore that must be P1. Correct? So do you think we have made any mistakes so far in all our inferences? All of them are based on known properties of the spline or the Bezier curve. We have not done anything that does not satisfy the conditions or the properties of the Bezier curve. Correct? I hope you see that. So now you have everything that you need to generate the curve. You know that n is equal to 2, you know k is equal to 3, you have the knot vector, and you have the three pi's, right? 1, 0, 1, 1, 0, 1. All these three are known. So which means in principle, you should be able to define this curve, which will be P naught. And I'm just going to write down the expression of the curve from what I know from memory, but you can go back and derive it if you want as a spline or a Bezier and convince yourself that this is the expression. Okay, this is a quadratic Bezier curve or a spline corresponding to this knot vector, and you will get this. You can go start from k equals 1, 2, and 3, and you will get this. So now is the question that if you take this expression, right, and you go from 0 to 1 and start plotting these points on an arc, right, as u goes from 0 to 1, do you think that it will exactly produce this curve? All the points will lie on this curve?
No, sir.
No, sir.
Does anybody think yes? First. Okay, if nobody is saying yes, then let me ask the two gentlemen who said no. Why do you say no? Because we have done everything correct, no? The endpoints are there, they are correct. We know that the curve has to be tangent to the first polygon leg and the last polygon leg, so that is also correct. That gives you only one choice of P1 that satisfies both these conditions, and that's the expression you get for that condition. Then why do you say that it will not match the curve exactly? What is your intuition or what is your reason?
So actually, one kind of intuition.
Yes, tell me.
It will kind of create, how to say, it will be looking like curve, but it won't be exactly a curve. Like
No, what do you mean to say is that it will be a curve that satisfies the given condition. That
yes,
cannot be violated,
sir.
of course. But all the points may not lie on the arc
yes,
of a circle, is what
yes,
you're trying to say.
Yeah, yes.
Okay, so that part is correct. That you will get a
So
curve.
I have done something on the Bezier curve. I have tried
Yes.
this example.
Sorry,
And when
go
I
ahead.
take u as 0.5,
Huh.
so the coordinate of the some point C, which I take here in the middle, does not come exactly which have the radius of 1.
Exactly.
So in
So
that way, I
that,
have
yes.
interpreted
So
that
you have already
expression.
done this and you have tested this. That's what you're saying.
Yes.
Okay, good. So that also is fitting with this observation that your other two colleagues are making, that while my resulting curve will start off at 0, 1 or 1, 0, it will go tangent to the line here and end up tangent to the other line and at 0, 1. But as you just pointed out, at u equals 0.5, I would expect the distance from origin to be 1, but I actually may get some other distance. Right?
Yes.
So that is correct. I think all the 3 points that you guys have made are right, which is that this expression does not represent the arc of a circle. Okay. So the first question is why? I mean, that we are not going to spend too much time on because part of the answer will come as we go forward. The next question is that then how can we get a representation for the circle which is somewhat similar to this so that I can have a single representation? Right now, why am I so fussy about having a similar representation for known curves also? See, when we started out this whole exercise, all these classes, we started out with the requirement that I have some arbitrary curve and I must be able to have a representation for that. Right now I have that. I have these B-spline curves, which is a representation for any arbitrary curve that you can think of. By just moving around these control points, you can get these curves. But now I'm saying that not only must these spline curves represent arbitrary shapes, they must also represent known shapes, which are my analytical curves. The reason for this insistence is, you may recall early on that we said that we want a single representation for all types of entities. Right? So if every curve that I know of is being represented by a polynomial which looks like Pi(nik) of u, then my utilities are limited, right? Are restricted. I don't have to write many utilities for finding length of the arc or intersection between two arcs, etc. So that's the motivation. That is why we are insisting that I must be able to define analytical curves also with an expression that looks like this. But here we are now proving that I cannot get a circle with a representation like this. So what kind of parametric representations of a circle are you familiar with? So if I say, fine, let's go back to coordinate geometry and let's look at parametric representation of a circle. What kind of representations do you think you will see? Are you familiar with any? Do you remember any from your coordinate geometry days? Would you agree that this is a parametric representation?
Yes.
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 Yes. And you have seen this, right? So you know, as u goes from 0 to 2 pi, you can generate the entire circle, or as you restrain the value of u, it'll automatically give you that quadrant or that particular section of the full circle. Right? Now, what is the problem with this parametric representation? Why are we not happy with this? One of the reasons why we are not happy with this is that it does not look anything like this. Meaning, this is not polynomial. Correct? This expressions that I have, it's a parametric representation, no doubt, but the representing functions, unfortunately, are not polynomials. Okay. So what can we do? If I were to insist that I want to write my circle as a polynomial in U, what can I do? Well, it turns out that again, you have seen the answer to that problem as well, which is an expression that looks like this. Have you seen this expression for a circle?
Yes.
Yes. And just to inform you, it comes from the fact that you can write cos u as a function of tan of u by 2, and same with sine. And if you replace the parameter as u equals tan u by 2, right, then you will get this expression. Okay. So this is a parametric expression for points on a circle. Again, as u goes from 0 to 2 pi, except that I have written it in terms of tan of half the angle as opposed to cos and sine of the full angle. Right? So that's the change that we have made here. But nevertheless, we have achieved one of the goals, that I want my expressions to be polynomial expressions. Except that I do not have a polynomial expression, rather I have my representation as a ratio of polynomials. Meaning this is a rational function, a ratio of two polynomials. Correct? Now this tells you one reason why you cannot have a spline or a Bezier type representation of the circle at all, because my splines are all only polynomial expressions. I have no way to capture the denominator terms here that I see with the expressions that I have, right? They will not work at all. And so, that's like a qualitative proof as to why you cannot have a spline or a Bezier exactly represent an arc of a circle, or for that matter, any conic curve, conic section. Okay. So, I mean, there are formal proofs, but I'm not just going to do that. I'm just going to ask you to look at this expression and the expression you see here, and you know that there is no way that I can use a curve that looks like this to represent a curve that has to look like this. Right? And so we know we have a problem. So question is, what do we do now? Right? What we do is we take up another form, right? And I'm going to write this. As that. Okay, so I have a new curve representation that uses the same basis functions as the spline, Nik. Okay, no change there. It is defined the same way. Nik of u is defined just the same expression, u minus xi by xi plus k minus 1 minus ui xi times ni k minus 1 plus same expressions. Okay, xi plus k minus u and so forth. No change, right? K is still the order, n is still the number of control points minus 1, right? And so forth. So nothing has changed except for the addition of this new set of parameters hi, one for each control point. Okay. Now, a little bit of algebra to convince you that this is the form that will work by writing down the case for k equals 3, n is equal to 2. I can write this as p of u equals h naught p naught into 1 minus u whole square plus 2 h1 p1 u into 1 minus u plus h2 p2 u square whole divided by h naught into 1 minus u whole square plus 2h1 u into 1 minus u plus h2 into u square. Okay. All I have done is just for this specific case, evaluated the basis functions and stuck them here. That's all I have done. Okay, nothing else. Now, we have, how many unknowns do we have in this equation now? What are the unknowns here?
H.
The three H's, right? So the three unknowns are the three H's. H naught is not known, H1 is not known, H2 is not known. Right? P naught, P1, P2 are known, right? You already calculated them. U is going from 0 to 1, so not a problem. So the only thing, three unknowns, three scalar unknowns, H naught, H1, H2. Right? And this, I will, now how do we solve for this? So let me just move this down a little bit, create some space. And what I will do right now is rewrite the same expression with the points in the x and y coordinates written in. So this is 1, 0 into 1 minus u whole square plus 2h1 into 1, 1 times u into 1 minus u plus h2 into 0, 1 u square divided by h0 into 1 minus u whole square right? This is my curve for the two control points, and I have written both the x and the y coordinate here. And this must be equal to 1 minus u square by 1 plus u square for the x and 2u by 1 plus u square for the y. And this must be true for all u belonging to 0 to 1. Okay. Now, this is a problem that you can solve, right? Because if this expression has to be true for all u's, then if I take the x coordinates of this, so I'll have this, this, and this, and I'll get one polynomial expression in u that must be equal to 1 minus u square. Then if I take the y coordinate, I will take this, this, and this. I get another polynomial expression, and that must be equal to 2u. And the third equation is I have this polynomial expression that must be equal to 1 plus u square. Okay, so I get three equations, and because it has to be true for all u, right? For every u, it must be true. That's when the curves will be identical, right? You can match the powers of u and equate their coefficients and solve for it. Three equations, three unknowns, you will be able to solve for the h0. And indeed, you will get h0 is equal to 1, h1 is equal to 1, and h2 is equal to 2. And this is a unique solution, because it's thing you can have different combinations of h1s also, but for this particular one, you get a unique solution, which is 1, 1, 2. So if I replace h0, h1, h2 by 1, 1, and 2 in this expression here, you will get every point on the curve to match every point on the circle. And as your colleague did, if you were to evaluate this curve at u equals 0.5, it will be bang on the circle. Okay, it will be bang on the circle. So this particular curve that I have defined here mistake. Okay, array. Yeah, so this is known as a rational B-spline. Okay. Now, remember, so this is a new curve that I have defined, right? That it is a rational B-spline, which has this form here, where the only addition from a regular spline is, my definition is somewhat different of the curve. Basis functions are the same, and I only have an additional parameter, hi, which is corresponding to every control point that I define, right? And hi are defined to be the weights, or what we call as homogeneous coordinates. This is just because you'll see it in these books. Weights are a good enough thing. Okay. Now, so that seems to satisfy your need for capturing the conic section. Okay. And what I want to do first is to highlight one thing, which is a shortcut, because we don't have the time to derive this. But remember, I said that for the Bezier curve, right? P of u equals pi bi comma n of u. I had shown you by a quick step that the sum of the basis functions, right, is equal to 1. I hope you recollect that, right? We showed this by the fact that, 1 power n is equal to 1, and I can write this 1 power n as 1 minus u plus u power n, and this is nothing but summation of these binomial coefficients, and therefore the basis functions add up to 1. Now, we can show the same thing for the spline also, but just by taking refuge in the fact that the spline is a particular general case of the Bezier, I will state this: Nik of u is also equal to 1 for I equals 0 to n. Okay? Which means that my basis functions in the spline case as well add up to unity. They are a partition of unity. Now, why am I needing this? I need this because if I go back to my expression for the rational spline curve, right? If I write it down for the case where all hi is equal to 1, what do I get? I get sigma pi nik of u, because hi is a 1, divided by sigma nik of u. Correct? If all my weights are chosen to be uniformly 1, then this is what I get. And what is this equivalent to? This is just equivalent to pi nik of u. Why? Because this, as per this observation, is unity. Okay? So what does that tell you? It then tells you that the rational B-spline is now the new superset. And the regular B-spline that we studied is a special case of the rational B-spline for all hi's being equal to 1. Okay? So we have now got a slightly higher class of generality where I have these weights associated with these control points. And the special case of that, where all the weights happen to be 1, is the regular spline that we have been talking about so far. So that's one good thing, right? Why? Because then I can cast every curve in this form and write this. Okay. The elegance actually will be more clear in a minute, but right now let me just stay with this. I want to just take a minute now, actually more than a minute, but this is something offline to just show you what the physical significance of the H naughts are, just so that you understand, right? Let me go back to the general quadratic curve, right? So I have a P0, a P1, and a P2, and this is my control polygon, and that's my curve. Right? Now I define a rational spline with a very interesting thing, which is that I choose my H0 to be 1 and my H2 to be 1, and I leave this floating. Okay. Remember, hi is something that you prescribe for each control point, and therefore this is how we prescribe it now. Earlier we calculated it for it to match the circle exactly, and we got 1, 1, and 2. Right? Now we are just leaving it to be that it be symmetric at the two ends and equal to 1, but the middle one is left floating. So I go back again to my expression of the spline that we have been seeing, quadratic spline, actually Bezier, and I rewrite this again as P0 and H1 is 1, therefore this is just 1 minus u whole square plus 2 P1 H1 into u into 1 minus u plus P2, and H2 is 1 again, u square, divided by the bottom I have 1 minus u whole square plus 2 H1 into u into 1 minus u plus u square. Okay, this is the case for this particular weight vector. 1 H1 1. Right? Just algebra. You don't have to worry about it. Just see the outcome of this. That's the more important thing for you to keep in mind, right? I now do something that your friend did for the question that I had asked, which is to evaluate this at P at u equals half. So let's say that point is this point S. Okay, so I'm finding S and I plug u equals half here, what do I get? So this is P0 by 4 plus P1 H1. I get a half and a half, 1/4, but there is a 2 here, so that becomes a 2 plus P2 by 4 whole divided by, this is half, so 1/4 plus 2 H1 by 4. So, okay, let me leave it as 4 right now. And this is 1/4. Okay. And so this becomes half plus H1 by 2, right? And so for simplifying it, I just write this. So S equals P0 plus P2 by 2 plus P1 H1 by 1 plus H1. Right? Because I get half plus H1 by 2, so the 2 goes up. I get a half here and 2 here, and this cancels out, and therefore that's what I get. Now P0 plus P2 by 2, I can define it here as the midpoint of this polygon leg, and I call it M, right? And therefore this becomes M by 1 plus H1 plus H1 by 1 plus H1 P1. Okay. So I'm going to rewrite this in a slightly different way. I will write this as 1 minus u times M plus u times P1. Actually, let me not say u. Let me take some different parameter alpha. I don't want it to be. Okay, so I'll call this 1 minus alpha plus alpha, where alpha is this expression, H1 by 1 plus H1. So you can quickly verify that 1 minus alpha is nothing but 1 by 1 plus H1. So that's correct. So here is the significance, I mean, the point of significance for us, which is that what does H1 mean for us? Right? So think of it here that this is defining a straight line between P1 and I couldn't hit neither of the points. So I'm going to blob it a little better. So that's what this is defining, this line, right? Now, as alpha is equal to 0, right? The point corresponding to u equals half is M. And when alpha is equal to 1, the point corresponding to u equals half is P1. Okay, that's straightforward interpretation of a linear interpolation equation here. But when alpha is 0, this is H1 is equal to 0. When alpha is 1, H1 is equal to infinity. Right? You can see that here. That if I stick this as 1, H1 equals 1 plus H1, and then you divide everything, and you will get H1 is 0. Right? Sorry, H1 is infinity when alpha is equal to 1. Rather, when H1 goes to infinity, alpha goes to 1. Okay. Now, what do we do with this observation? This tells you what the significance of H1 is. So H1 tends to pull the curve towards the control point P1. As H1 increases, the curve gets pulled towards P1 and of course passes through the point when H1 is infinity. On the other hand, when H1 is 0, it goes and snaps away, farthest away, which means this polygon leg. Why can't it go below this? Can anyone mention why? Because it will violate what property of the spline curve? If my curve goes below this, what property will be violated? The convex hull property, right? Because now if the curve has to be, inside the convex hull, then it has to be within the triangle, and therefore the farthest it can be for the lowest value of h1 is this point here. And the highest, when h1 reaches infinity, it gets pulled through the point p1. So that's the significance of the homogeneous coordinates h1. Okay, that's point 1. Now, the next point is more interesting one, but I'm not going to prove it here, but I'm just going to say that for different values of h1, so when h1 is equal to 0, 1, h1 is equal to 0, you know what is happening. But when h1 is equal to 1, the curve becomes a parabola. When h1 is greater than 1, the curve becomes a hyperbola. And for h1 equals 1, less than 1, it becomes an ellipse. Okay. Again, I'm stating this without proof, but believe me that there is a way to prove this, not very difficult. Okay. But the more interesting thing is that if I know the angle subtended, right? So if this is the arc, right? We know that somewhere between 1 and 0, right? Between 1 and 0, there is a point, a value of h1 for which this is an exact arc of a circle. So if the angle subtended by the arc of a circle, right, is 2 theta, then for h1 equals cos theta, right, which is you get arc of a circle subtending 2 theta. Okay. Now, so what does it mean? Let's revisit the example that we had earlier of the quadrant of a circle and see what it does for us. So I have this, I have that, I want 90 degrees. This is center 0, 0. My first control point is 1, 0. The second control point is 1, 1. And the last control point is 0, 1. And that's my control polygon. Right. So the picture I have drawn looks like this here, in this one. Right. So because this line is horizontal in my picture right now. But for this, now if I use h0 equals 1, h2 equals 1 by root 2, and that's nothing but cos of 45 degrees, and this is equal to h1, and h2 equals 1. So this says that for this set of h's also I will get an arc of a circle exactly. Right? So what's the difference between this and what you solved for earlier, right? Where I got this, but instead this one was 1, h1 was 1, and h2 was 2. I said that both are giving you circles, exactly. But what is the difference then between these two? What do you think is the difference? Any thoughts? Any ideas? Where do you think the difference can be? If both are exactly a circle, arc of a circle, both start and end at the same place, perfect. Every point is one unit away from the center 0, 0. Then what else can be different? Okay, it's telling me that the time is getting up, but nevertheless, let me just leave one thought with you. Remember, we said that the curve is a mapping, right? From the parametric space, this is U, to the real space, right? So I have a point U here, and it corresponds to a point U there, and it corresponds to a point U there. But the difference in the two cases is that in one case, when I am at exactly 0.5 here, right, in the midway, I'll be exactly at the midpoint of the arc also here, which means that angle subtended there at that point will be 45 degrees. Whereas in the other case, it may be slightly off. Right? That's the difference. All points will be on the curve. There will be no problem there, except that in this case, if I am 0.1 here, it will be exactly 0.1 of the angle there. 90 degrees, 0.1, 9 degrees, it will be there exactly. If it is 3/4, it will be 3/4 of 90 degrees right there, man. Here, it may be off a little bit, right? 0.5 will not be exactly at the center of the arc. 0.1 will not be exactly at 10% of the arc. 0.75 will not be exactly at 3/4 of the arc. So which means that in one case, as I'm traveling from 0 to 1, the curve also travels at the same speed, right? If I am at midpoint here, I'm at midpoint there. Here, it travels at slightly different speeds. It may go faster sometime, then slower, then faster, or slower, faster, slower, whichever, right? Which means that my points will accumulate like this, then sparse, then again accumulate. Or it may be very far away in the beginning, then accumulate in the middle, and then again this very far. So this will give you a uniform parameterization, meaning that a point at the middle will be a point in the middle here as well, whereas this will not give me a uniform parameterization. That's the only difference. Otherwise, both are identical arcs of a circle. There is, of course, a nice symmetry here. The first and the last control points have weight 1, and the middle one has some 1 by cos theta. Sorry, what am I saying? 1 by cos theta. Cos theta. 1 by root 2 is the value of cos theta. Sorry. Here, that it is a little asymmetric, 1, 1, and 2. And we will see the significance of that in the next class. So let me now leave you with a question, and then we will pick it up on Wednesday. So now you know how to define the arc of a circle that is subtending an angle of 90 degrees. Now, what about an arc of a circle that is subtending an angle of 180 degrees? Okay, so now you need to think about this and let me know if you have any answers in the next class on Wednesday. Okay, so I will stop here, and again, we will take questions. If you have any immediate questions, please ask me now. Otherwise, we will do it after the recap on Wednesday. And then we will continue with this question, that now that you know how to represent an arc of a circle subtending 90 degrees, how do I represent a circle that subtends arcs of a circle subtending 180 degrees?
So,
any quick? Yeah, please.
Sir, right now we kind of validated that with only 3 control points, we need one additional H1
Yes.
parameter to define the
Yes.
correct arc. So
Yes.
what if we are already defining it using 4 control points? Like I tried it, but the issue was that I have 2 unknown points. So that's why I dropped the idea.
Yes. Okay.
Sir, adding to this point, I have also seen somewhere the 4 control points quarter circle curve, but they have some intuition that the point lies at that place and that place. So it was a bit difficult to understand with the 4-point curve or the cubic equation of the quarter.
What you are saying is that how do I get a cubic to represent the arc of a circle?
Yeah. Yes.
Okay. I don't know if you remember, right, in when we were talking about the limitations of the Bezier, right? I had mentioned that you can, introduce a new control polygon where one control point is on this leg and another control polygon point is on this leg. And so the new control polygon, let me just take a different color, sorry. So one point is here, sorry, one point is here and the other point is here, so that my new control polygon is that. Okay. And the claim that I'm making now to you is that this 2 points I can find by some linear interpolation between these two and these two. And the resulting control polygon, which has 4 control points, and therefore a cubic Bezier curve, will represent the arc of a circle exactly. That's how it works. Okay. And let me give you a quick intuition. If you go back to your expressions for the Bezier, you will see that the derivative, right, takes the form n times at, let's say at 0, takes the form n times p1 minus p0, and at 1, it takes the form pn minus 1. Okay, this term will come here. But this is, you can, for quadratic, you will get 2, for cubic, you will get 3, and so forth. So you can derive this by hand. And induction will tell you that for n, it will be n. Okay, so now it's very easy, right? Because you know that the tangent value here for the quadratic is twice p1 minus p0. And for the new curve, it is thrice q1 minus q0, right? And q0 is the same. q0 is equal to p0 from the property of the Bezier curve. And therefore, I can solve for q1 from this expression, right? And it will be exactly 2/3 or 3/4 of the way from here. 3/5 of the way, sorry, not 2:3 is the ratio. So 3/5 of the way from here. Okay, and that's how you do this. And you can keep doing this for higher and higher curves. So the next time around, if I want to break this up, I introduce a point here, so that will be a 4th degree curve. Therefore, its derivative will be 4 times r1 minus r0, and the current derivative is 3 times q1 minus q0, and therefore q0 and r0 must be the same, so I can calculate r0. Right. So that's how you will get higher number of control points defining the same curve. I hope that answers your query. So if you wanted 4 points to define the curve, this is how you would get it very easily. 3 you will get from geometry, and 4 and 5 and 6 you will get purely from the construction here. Remember, I had referred to this as degree elevation. So there is a formal algorithm that you can use and get as many number of control points you want. Yeah.
So just one comment. So actually, I observed this kind of, it was forming in an octagon, like a circle was subtended across an octagon shape.
Okay.
So that way I just clicked that.
No,
maybe.
So remember, you're talking of a circle or an arc of a circle?
No, sir, I got the idea from there. Like.
No, but the picture that you saw, was that for a full circle or for an arc of a circle?
It was for a full circle, sir. Full
circle, yes. So just park that thought with you. We will come back to that also.
Okay.
In fact, your answer to this question that I asked just now, about the semicircle, you won't have a single answer to this. Right?
Yes.
And that will lead to an answer to the question you are asking as to how I can get that many type of control points to define a circle.
Okay.
Okay. Yeah.
Thank you.
Fine. I'll stop here. Yeah. Anything else? Okay. If not, then I'll stop here, and we will pick it up from this question after the recap and other questions on Wednesday afternoon. Thank you.
Thank you.
Sure. Thank you, sir. Bye, sir.
Sure.
Happy Holi, sir.
Same to you guys. Yeah. Be safe. Don't waste too much water and have fun. Yeah. Thank you.
Sure, sir. Bye, sir.
Bye.